So, hello everybody and welcome to Java Performance Optimizations talk. Today we're going to discuss about some of the optimizations that happens during the runtime inside the hotspot in particular, but all the things that we discuss in here are also valid for the OpenJDK because it's mainly the same source code. My name is Ionut Balosin. I'm currently a software architect for Luxsoft. Overall 10 plus years of software development experience, in particular very keen on performance and tuning topics, plus software architecture. I'm as well the technical trainer inside the training department in Luxsoft, and as well conference speaker. From time to time I write some articles on the performance and software architecture. Our agenda for today, it's a bit, contains a lot of topics. We'll start with just-in-time a briefing introduction about what means the JIT, and after that we'll go through a few optimizations, starting with uncommon traps, null sanity checks, and we'll see what's happened during the runtime in regards to this optimization. So how JIT behaves to benefit of the best optimizations. What's in for you to take away out of this talk? It's a better understanding about what happens inside the hotspot virtual machine from the just-in-time compiler standpoint. As well, you will learn few just-in-time compiler techniques, how JIT triggers those optimizations. And at the end, we'll go through some cases when just-in-time compiler it's not able to compile anymore the code. So we will see some corner cases which prevent the just-in-time compiler to optimize our code. In a nutshell, it will be useful for you if you want to tune to squeeze the ultimate performance out of your Java application. Few things about my configuration, because during this talk we'll study a lot of we'll go through a lot of tests. So a few things about my hardware configuration. I was using i7 Skylake processor with 16 gig of RAM. From the software perspective, all of the tests were done on Ubuntu, but of course I used as well Windows just for the sake of this presentation. The JDK was the last one, the last official one, 1.80, update 1.1, and I was using a JIT watch tool and HPJ meter just to prepare the talk. Okay, so few things about just-in-time compiler. It's a very brief introduction just to put a bit the context. What we have during the runtime, it's mainly the JVM with the execution engine. The execution engine made of the interpreter and just-in-time compiler. Of course, there is a class loader, garbage collector, but it's not our interest for today. We were mainly focused on the just-in-time compiler for today. Just-in-time compiler, if we have to zoom in a bit, it's made of the client, the C1 compiler, which triggers only rock-solid optimizations based on the invocation threshold, which is around 1.5k iterations, so it's around 1,500 iterations. The second one is the server one, which does better optimizations in regards with C1, but it needs a higher threshold, so it's around 10k iterations to trigger and to compile the code. And as well, we have a tiered mode, which is a mixture between C1 plus C2, and it has a lot of tiers. It starts in interpreter, it goes in C1 without profiling, with basic profiling, with full profiling, and it reaches the second one. If we have to take a look over the speed, of course, in the interpreter, we have the lowest performance speed out of the Java code that we wrote initially, because mainly the bytecode is interpreted. The second level, I would say, is the C1. In the C1, we might have around 5 times speed improvement in comparison with the interpreter, and the best one is the C2. In some cases, it might reach like 100 of times more than the interpreter. But of course, it does a lot of assumptions. It as well do a lot of the optimizations, so it needs more context. By context, I mean more number of iterations. All of this being said, just a bit of context, let's dig into the optimizations one by one to see what's happening under the hood and what just-in-time compiler does in order to do that. Just as a remark, during the next optimizations we'll take a look over the Java code and the assembly code. Why? Because the assembly code it's more interesting. Based on the assembly code, we will figure out what's really happening under the hood, and for us to have a better understanding about these optimizations, we definitely need to understand the native code. We will skip for this talk the bytecode. Okay, the first optimization or technique, I would say it's more a technique, it's called uncommon trap. What's an uncommon trap? It's mainly a situation which is unlikely to happen inside during the runtime inside the hotspot, which means that just-in-time compiler treats it as a check. If this check is happening, it bails back into the interpreter. This is mainly an uncommon trap. It's mainly a situation unlikely to happen, but when it happens, the just-in-time compiler bails back into the interpreter. To understand it better, let's see this very trivial example. What I did here, I created a loop. Inside that loop, I iterate through the loop 20k times, yes. And inside the loop, I call a hot method all the times with true. The hot method, it's like in here, it receives the boolean, and based on it, if it is true, it returns 1. Otherwise, it returns true. And returns the counter. Why I chose here 20k iterations? Because I wanted to be sure it reaches the C2, the second level, and as well to benefit out of the best optimizations during the runtime. And I took out this code and I launched my JVM in here with print assembly. Print assembly says for the JVM I want to print my assembly during the runtime. And of course, I want to print the assembly in the Intel syntax. There is as well AT&T syntax, but for me, I more use the Intel. It's mainly the same, but it's just a matter of representation. And I disabled the tier compilation, which means in our context, I was using only C2. I don't want to go through the C1 compiler. I want to reach directly the C2. I'm not interested in all the intermediate optimizations, only in the final ones. And of course, the last one, it's my class. And if we scroll and zoom it a bit into the assembly code, of course, I really simplified for this talk just to be easier to be understandable. What we have here, we have the hot method, which receives my boolean. It's this RDX. It compares the RDX with 1. If it is not equal, we see here it does a jump. But if it is equal, it returns true, which means if my method receives 1, returns true. But if it is not the boolean, it is false, it does a jump. And this is the jump to an uncommon trap. What's an uncommon trap and how it works? Because I called my method during the runtime only with true. The hot method was called only with true for 20k times. The just-in-time compiler assumed that there is an unlikely situation to be called with false, and just-in-time compiler added an uncommon trap. And uncommon trap, it's mainly a call to this address. When it happens, just-in-time compiler locks the method, marks as not being entered, and switches back in the interpreter. So based on this, we can see that JIT, just-in-time compiler, optimized at the moment only for the true branch. And for the false branch inside the code, it put this uncommon trap. If we get back to our initial snapshot of the code, we see that we have the hot method called only with true. It got optimized, it got compiled, and if we have to measure just one iteration after it reached the C2, on my laptop at least, it took around 300 nanoseconds. But the question is, what if I call my hot method with false just immediately after? Calling the method with false just immediately after and measuring the time elapsed, we see that one iteration took like 100 times more than the previous one. And it leads me to the question why. What happened under the hood inside the JVM from the just-in-time compiler perspective to have such big difference between these two calls? Just two calls in a sequence. To spot out what happened, we have to redo the test. Relaunch the test mainly, and this time I was using pre-compilation because I'm interested in all the things that happens under the hood. I want to see what was compiled, what was disabled for the moment. And if we check the output for the hot method in here, we see these two lines. But what it means, because apart the trivial methods, we see a lot of other information. The first column corresponds to a timestamp. It's mainly the number of milliseconds since the JVM has started. The second one, it's mainly a compilation ID for the just-in-time compiler. The third one, that percentage, it stands for on-stack replacement. What's on-stack replacement? For example, if you have a method and inside that method you have a long-running loop, that long-running loop could trigger the compilation for that method. This context is the context of on-stack replacement. What happens during the runtime, the stack frame, it's replaced by a native stack frame on the stack. Another thing is this around 4, which is mainly the bytecode index which triggered the on-stack replacement. So it corresponds to this percentage and the number of bytes that got compiled. Okay, so getting back to our scenario after this explanation, we can see that when we triggered the method with true, it became compiled. The hot method initially became compiled, and because and as well inlined, and because we have a long-running loop inside our main method, the main method itself was compiled, and this compilation was triggered from the on-stack replacement perspective. What happened afterwards, immediately when we called just once with hot method or false, we see here this mark which is saying not made not entrant, which means all the assumptions, all the optimizations made previously when the method was called by true are not valid anymore. So mainly the uncommon trap was hit and the method was bailing back into the interpreter. That's why there is that big discrepancy, like 100 times more when I called once with false in regards with the previous one. If we have to illustrate a bit from the thread's perspective what's happening during the runtime, initially we had our hot method was starting in interpreter. After a certain number of iterations, the C2 compilation level was reached. The method was compiled, but when we called with false parameter, we hit the uncommon trap, which means at the runtime we bailed back into the interpreter. That's why we had that big discrepancy between the time elapsed. The question is, what happens, for example, if there are other threads running the same version of my hot method? The answer is that if the other threads run in the same time the same version which was compiled, and if they don't reach the uncommon trap, they continue the execution. But if I have another thread like in here which calls my hot method afterwards, after one of the threads reach the uncommon trap, it starts from the interpreter from the very beginning. So this is the explanation what's happening during the runtime. Now what I did, I continued my experiment and I optimized with true and false. I also included hot method of false into a long-running loop, and I checked the compilation. And in here what we have, it's the the first two lines are very similar to the previous one, which means we had the hot method, it was compiled. We have here an on-stack replacement for the main method, so the entire main method was compiled. And when we triggered the hot method just once with false, it became not entrant, but because we have this long-running loop in here, it became again optimized, and it was compiled, and as well it triggered again the compilation for the main method. So as you can see, during the runtime, if you are using the C2, there are a lot of optimizations, deoptimizations. Just-in-time compiler, it's eager to do a lot of assumptions just to make the better optimizations for our code. Going further, if we have to take a look over the assembly, if I have to run with print assembly as we did before, we see here in this case we have this C conditional conditional move not equal, which means in this case after we hit the uncommon trap, the just-in-time compiler falls back to the traditional way of handling these checks. So if the just-in-time compiler has the context of being able to reach both branches, branches for true and branch for false, it doesn't do any more uncommon trap, and it switches back to the common way of handling this, using mainly jump instructions. That's about the uncommon traps. Some sort of summary for you. So if a conditional statement was following only by a single branch, an uncommon trap, it's a good idea to optimize this during the runtime, as we saw. The thing is that once the uncommon trap it's hit, the just-in-time compiler have more context. So in this case, it doesn't do any more uncommon traps. And just to summarize, the uncommon traps, they are a good solution to optimize the code during the runtime. But since they are hit while they are while the thread is hitting the uncommon trap, it's costly. It's costly because it has to deoptimize, it has to bail back into the interpreter and starts the execution in the interpreter. Inside the hotspot, there are a lot of uncommon traps situations, and for this talk I took out of them the null checks. How hotspot handles the null checks. For this, I took this code, again, the hot method, the same method, and I'm calling with an integer which is not null. And inside the hot method, I say if my integer it's not null, multiply and return the result, otherwise return 0. So I have this null check. What we have during the runtime? During the runtime, again, I started my program. When the JVM was triggered, I set print assembly because I wanted to check how it behaves from the native code perspective. And as we can see here, the assembly code is very, very simple. It has mainly, after I clean it a bit, it has this move and this EAX multiplied, this bit operations, sorry, which means mainly put the value from the integer in EAX and does the multiplication by 2. There is no null check explicitly added in the assembly code. Why? Because as we can see here, there is an implicit dispatch to this address in case there is something wrong. What could be wrong? It's mainly a segmentation fault. Imagine the C or C++. What's happened when you call something which is null? You got a segmentation fault. It's implicitly handled by the hardware, And in this case, once the segmentation fault is in here, we have a null handler for our uncommon trap, and again it bails back into the interpreter and starts from there. So in this case of handling nulls inside the code, there are no explicit checks. Instead, the just-in-time compiler leverages on default OS signals, segmentation faults, for example. When a segmentation fault is happening, it is caught by the OS, it is handled by the JVM, and inside the JVM, it is, for example, there is a decision if null pointer exception is thrown for the programmer, or if it is not the case, as we see here, because we have an explicit null check in our code, it bails back to the interpreter and starts the execution. If we have to optimize a bit more, so we call the method with null, and after that immediately 20k times with a value which is not null, and we have to print as well the assembly. We see here the test, it's explicitly added. What it's in here, mainly we test this RDX, which is the parameter our integer received. If it is null, there is a jump in here for L001 label, and in here it's a XOR between the same register, which means return 0 basically. And we have a jump to another label, which is the return of our method. But if it is not null, it's the same code as we did previously when the null was implicitly dispatched to that address. So this is the way of relying by default on signals inside the JVM, particularly for this case of dispatching or of handling mainly the null checks inside the JVM. But after the moment that our code reached the null, there is no any more uncommon trap, as we see here. It's an explicit check. Just to sum up, null checks relying on signals are natively handled by hardware and as well by OS, and very well handled by the JVM. But in case they are triggered, of course, it's costly. It's costly because you have to pay the cost of catching the signal, the segmentation fault signal, handling it, bailing back into the interpreter, and continuing the execution. And as a conclusion, don't let null happening a lot in your application, because especially the first time you will have a lot of segmentation fault signals triggering under the hood, and after that, after these segmentation faults are triggered, the code is recompiled by this time with jump instructions. So there inside the code there is those test conditions, which might be costly as well. Another kind of optimization, it's called devirtualization. What's devirtualization? It's mainly a technique to turn polymorphic calls into direct calls. What it means, for example. On the right side, we have a parent class, which is called CMAT, which has a method compute, which which receives an int, and it is extended by elg1. This elg1 is the first implementation. It's mainly an extension of this parent class. And if we have to test it, I put this in a long-running loop, and inside the long-running loop I call the hot method in here, and inside the hot method I say mat.compute. And what it does internally, mat.compute, it returns the I multiplied by a constant. So very basic implementation. And afterwards, I started my program again with print assembly, because I was curious what's happening, how just-in-time compiler handles this these virtual calls, because mainly it's a virtual call, it's a polymorphic call. If we zoom it inside the assembly, we see very simple things. Here it's mainly the first line, it's mainly a conversion, and on the second line it's mainly the multiplication. So it just receives something, it does the conversion to double precision, and afterwards it does the multiplication, and it puts the value inside this register, and it is returned back afterwards. As we can see, there is no check if my instance during the runtime is of type ELG1. So, which leads me to the conclusion that this case of polymorphic calls, if they have just one single target, which means single target monomorphic calls, they are inlined, and the just-in-time compiler doesn't add any uncommon trap for them. Let's see, if we go further, what we have in case we add the second implementation, and as well we enrich our test by this instance, and this instance calls the same hot method in the loop, running loop. If we check the native code, it's a bit more complex. A lot complex, I mean more instructions added, and in this case of two possible targets invocation, just-in-time compiler adds explicitly the check. What it does, for example, it checks if the instance is of type ELG1, which is in this compare. If it is of type L1, it jumps in here and it does the multiplication. After that, if it is not the case, it compares with ELG2, if it is an instance of ELG2, and if it is not the case, it jumps in here and it triggers the uncommon trap. So mainly, if there is an instance of not ELG1, neither ELG2, I have to trigger the uncommon trap. But getting back, if the instance is of type ELG1, it does as well this multiplication. So mainly in this case of bimorphic calls, two target calls during the runtime, there was inlining which was occurred, so the just-in-time compiler did the inlining and as well added an uncommon trap for the possible third or fourth extension of my parent class. Let's see now, let's go further with this, and let's see what happens if we extend with the third implementation, the same base class, and as well we enrich our test, and we call the test with the hot method with ELG3 and I. In this case, if we print the assembly, it's very, very simple. It's simple because it contains just a virtual call to the hot method, which leads me to the conclusion that the megamorphic calls are mainly the calls starting with the third implementation. The just-in-time compiler neither inline nor do any uncommon trap. It just does a virtual call, which is even more costly than in case of bimorphic calls and monomorphic calls. If we have to reiterate on it, monomorphic calls are inlined without any uncommon trap. Bimorphic calls are as well inlined as we saw, but there is an uncommon trap added in the code. The just-in-time compiler adds a check. If the instance is not of type ELG1, neither ELG2, I trigger the uncommon trap. And megamorphic calls are handled as virtual calls. The just-in-time compiler doesn't do any optimization. It just triggers the virtual calls. In reality, what's the cost from, for example, from one monomorphic to megamorphic call? It's around several nanoseconds. I would say during my test, I spot it out as being like 3-5 nanoseconds. So anyway, it's very performant in any case, but you should have this idea in mind that once you reach the third and the fourth and the sixth implementation, it becomes more costly because it has to resolve the virtual calls during the runtime or upon each method call. The next one is called loop unrolling. What's loop unrolling? It's mainly a technique to reduce the number of jump instructions if we have long-running loops. For example, what we have in here, we have a method, and inside my method I compute the sum of this array. And at the end I return the sum of the array. If I have to compile and see the print and see the assembly, as we see, there are a lot of additions. A lot of additions inside this loop. It's from here to here, and the counter increases by 8 mainly, which leads me to the conclusion that the just-in-time compiler did a loop unrolling, and it unrolled the loop by 8 iterations in the same time. This is a very powerful technique because, for example, in case you don't have data dependency between all of these addition statements, there might be parallelized and run in parallel. And another important thing is that, as you see in here, it starts from 1. Even if my initial sample case at the Java code level, I started from 0, which is another technique. It's called loop peeling. So what mainly does the just-in-time compiler during the runtime, it peels out of the loop only the first iteration to do some checks. For example, it could be useful as well for memory alignment, and putting aside the first loop iteration, it iterates and parallelizes the number of additions. And as well in here at the bottom, if there is some remaining, for example, if my array it's not a multiple of 8, it triggers here the remaining out of that list. And if I have to put it into pseudocode, it looks like this. The loop peeling, it's the first iteration, and from the counter of 1, it does 8 additions in parallel. And here at the bottom, it triggers it handles the remaining of the sum operations. Which leads me to the question for you, because we are aware, we have in mind this sort of loop unrolling technique. Would it be useful for us to be a bit smarter in advance? For example, having an array and instead of iterating one by one to do the sum, to put like four additions in the same loop iteration. What do you think? Would be a good idea? Mm-hmm. Okay. Any other guesses? It could do better. Yeah, so thanks. Let's see how it does. How the just-in-time compiler deals with this some sort of eager optimization in advance from the programmer perspective. I don't print again the assembly because it's a bit more complicated. I try to translate it into pseudocode just to be easier for us to understand. And the assembly code look like this. It did as well the loop peeling, so it peels the first iteration, which means the first 4 additions. So starting from fourth one, it did the same. So what it did, it mainly reloop what I did, because it thought it's not a very efficient way of doing loop unrolling, and it did loop unrolling in a more efficient way that I did in the beginning. So which means mainly it reloop my loops and it unroll them again. So at the end, in this, we end up with a certain number, the same number, sorry, of iterations. But just to tell you that the assembly code, it's much more complicated. So we try a bit to put the just-in-time compiler into difficulties, which leads me to the conclusion that it's not quite a good idea to do this kind of optimization in advance. So let the just-in-time compiler do them for you, because just-in-time compiler knows better than us during the runtime, especially for this case, for the loop unrolling. Loop unrolling as well, just to sum up, it's a good technique because it reduces the number of branches and as well the number of jump instructions, and also opens the door for instruction level parallelism, which might allow basic block level vectorization optimization. And as we discussed, avoid this manual loop unrolling, because let the just-in-time compiler do them by itself, because he knows better than us what's in compliance with the hardware platform, to your CPU, to the number of cores, to the number of threads, how to do it better, in a better way. String deduplication is the next optimization that happens during the runtime, which mainly says that if I have the garbage 1 enabled and starting with Java 1.8 update 20, during the runtime, during a GC cycle, the garbage collector searches for strings backed by the same char arrays. And how it searches, those char arrays, the strings, sorry, should have the same hash code and the same char array. And if there are some similarities, if there are strings that are backed, all the redundant char arrays are removed. In this case, it optimizes the memory footprint during the runtime. Having this sort of explanation in mind, I did some tests on my machine, and what I did in here, I created a very simple application. I created a lot of strings, and I set a threshold for my heap memory to 1 gig. And because I wanted to benefit out of the string deduplication optimization technique, I as well explicitly set the G1. G1 is not enabled by default in 1.8. And I did 2 types of tests. The first test was with string deduplication, and the second one was without string deduplication, as you can see here. So what we had from the stop the world pauses, in case of string deduplication, the red one, we see a bigger number. So the number of stop the world pauses took more. Stop the world pause took more. Why? Because after a certain number of GC cycles, the G1 collector had a bit of work to do in comparison with the blue scenario where I deactivated the string deduplication. So it had the work to do of finding the strings and removing the redundant char arrays from the main memory, from the heap mainly. So in this case of context, we say that string deduplication may add, not may add, it adds definitely longer stop the world pauses during the runtime. But it is also beneficial, and in my case it was beneficial because if we get back to this bounded amount of memory, in case we use string deduplication, the memory was was reclaimed during the runtime, and I was able, my application ran for a certain number of cycles more, because I had more heap to allocate more strings, in comparison with the previous case when I gotten out of memory earlier. Why? Because in the heap memory I had a lot of redundant char arrays. So it's useful in this case. And if I have to take a look as well over the heap memory usage, I see in here, without string deduplication, I see here the heap usage after a GC cycle was bigger than the heap in case of using string deduplication. Just to sum up, string deduplication reduces mainly the memory footprint. It's a good technique. It was added in the JVM just for this, to reduce the amount of heap, and it's very useful in case you deal with bounded amount of heap during the runtime. But it impacts performance. It impacts performance, as we saw. The stop the war pauses take more, of course, because G1 has additional work to do in regards with reclaiming the char arrays. Biased locking. Bias locking, it's in there since 1.6, which says bias locking, it's a technique in case of uncontented locks. For example, I have a synchronized method, but during the runtime I have just one thread that calls it. There is an optimization which avoids the penalty of the real synchronization. This penalty of real synchronization relies on OS mutexes, conditional variables, signals under the hood, so a lot of stuff under the hood that it's triggered by this synchronization on locks. And the technique says don't go real synchronization, just bias the lock towards the thread it owns it. I did as well some tests to check if this bias locking scheme impacts performance. In my case, what I created like 50 threads. Inside each thread, I put a synchronized on the shared instance, and each thread locking on the same shared instance, incremented a counter. I started my threads in here and I joined for all of them. And if I started my JVM with bias locking startup delay 0, why is that? Because by default bias locking scheme, it's active after I think 4 seconds, so it's not activated, it's not enabled from the very beginning. So I started my JVM with 0 because I want from the very beginning, just for the sake of my tests. And I printed the application's stop the word pauses. And as we can see, the GC output, it's a bit verbose. It contains a lot of total time for which application threads were stopped. So a lot of them. I did a sum. And in my case, it's around 1 millisecond. Which means this millisecond was mainly spent in operations like revoke bias and enable bias locking. So we pay a lot during the runtime, 1 millisecond, mainly for this bias locking mechanism. I did the same test again, but this time I disabled biased locking. I disabled it from the very beginning, and here the output is more clear without any stop the word pause. So around 0 seconds approximately. So 0 seconds, which leads me to the conclusion that biased locking, it's a good technique. It helps you a lot in cases where you don't have contention. But if you have contention, you pay a lot the cost of the stop the word pauses. So that's why mainly a recommendation for you, if in your application you have to deal with a lot of threads, there is contention, maybe it would be better to disable the bias locking scheme, because you have to wait for the stop the word pauses during the runtime. Another technique, it's mainly the inlining, and today we are going to check, to study the concurrency implications in regards with the inlining. What's the inlining good for? The first answer, it will be it saves us from the pop and push overhead, but it's just, let's say, I would say, very naive explanation. It's not like that. In reality, there are a lot of benefits. The first one is about the consistent control flow of the code. If just-in-time compiler sees that the code is consistent, the flow of the code is consistent, it relies to move it around and deals with optimizations. It deals a lot with optimizations across boundaries. For example, caller and the callee. If the caller and the callee can be inlined together inside the big piece of code, it does optimizations. And as well, if we can inline something, in some cases it saves the number of memory loads. And immediately we'll see what means this kind of technique. To dig in inside it, first a bit of context about the test scenario. Again, the same long-running loop, but this time inside my hot method, I called height method twice and width method twice. So it's mainly a call to reference a variable out of the memory, let's say, and store it in these locals. And at the end, my method did some multiplication and addition and returns the result. What we have in here, because between these calls on the height and on the width methods, we explicitly call in between a method which can't be inlined anymore. What means can't be inlined? A method that just-in-time compiler cannot inline, so the caller can inline the callee body. In my case, how it looks like, it's a bit funny, because I created it in an explicit way to prevent the inlining from the gist perspective. So it means, for example, it calls M2, M3, M4 up to M11, which at the end it returns 0. Why I did that? Because implicitly the HotSpot JVM has a parameter which says max inline level its default 9. So after the 9th level of call depth, just-in-time compiler is not able to inline our code anymore. Having this said, if we get back and we run our example and check the assembly, what's in here, we see the explicit call for the height method to retrieve the value. We see this virtual call to the method which can't be inlined, and again the same call to the height method. And if we continue zooming into the assembly, it repeats the same call to the same method which can't be inlined, and twice, two calls mainly the width value, twice width values out of the main memory. Why is that? Putting it into a bit of generic context, if we have two memory retrieval, but in between we have a method that just-in-time compiler can't inline that method, the just-in-time compiler assumes that there might be other threads that change the memory. So it explicitly forces a new reload from the main memory from this height value. That's why we have twice calls for the height and twice call for the width. If we repeat the test and we increase the default max inline level just to be able to inline that method, we see the native code. It's like in here. It does only once the retrieval from the height memory and just once the retrieval from the width, and as well the memory the method can't be inlined was inlined. So this is a very, very interesting technique to keep in mind, because if we deal with methods that can't be inlined, you prevent a bunch number of other optimizations. So for you to check inside the code, it's mainly based on the size. There are methods that if they are bigger than 35 bytes, they are not inlined, even if they are called more than 250 times. And in case you have so in case you have frequent methods, for example, hot methods, those methods are not inlined anymore if they are bigger than 325 bytes. So be careful with this, because you prevent inlining. So preventing the inlining, you prevent any other optimizations during the runtime. As well, the max inline level, the call depth level that we discussed about, it's 9 by default. And there is a max recursive inline level for recursive calls, which is set to 1 by default. How to check in your code, just a very straightforward technique. There is a jar called jar scan, so you can check out of the code base on your side which methods are not eligible to be inlined. Because their size is greater than 325 bytes. So it's a very straightforward technique that recommends you what to refactor out of your code in order to allow inlining to happen during the runtime. And the last part of the talk, it's in regards with methods that don't JIT. The first case of such method, it's a method which has a huge body. By huge body, in this case, it's a body that has 805 bytes. So for this case of methods, of course, the example is a bit exaggerated just to prove they are not compiled. And if we have to run this, and as well to print the compilation, as we see here, there is nothing which got compiled during the runtime in regards to the hot method, only the main method. If we have to check inside the JIT watch tool, we see written in here, no JIT compiled. That's why. Why is that? Because there is a flag inside the machine which says don't compile huge methods, which is enabled implicitly to true. But what is a huge method? A huge method, there is as well a task for the OpenJDK. A huge method, it's mainly a method that has more than 8,000 bytes. So in this case, they disabled implicitly their compilation because, as it is written here, they are not well tested, and probably they'll have more other implication in regards with the code cache, to the flashing policy on the code cache. So if you have such huge methods, it's better maybe to refactor them, because turning off don't compile huge methods might cause any other side effects. The next corner case of method which are not compiled anymore are methods with a lot of arguments. In here we have methods, for example, with 70 doubles, very, very big signature. And the return is very simple. It returns the sum of all. In this case, if we have to compile, with the just-in-time compiler prints this kind of warnings saying that unsupported incoming calling sequence or unsupported calling sequence. If we search on the web, there is also a task for the OpenJDK. It's still in open. I think it's there since the very early version, the sixth one. It's moved towards 10, so probably there is a rumored improvement on their side in regards to these methods. So all of this being said, I want in closing to end up with a quote from Richard Feynman, which is a guy which really inspired me. It's a very, very smart, was mainly very smart guy, and he said that it doesn't make a difference how beautiful your guess is, how smart you are, who made that guess. If it disagrees with the experiment, it's wrong, it's nothing. That's why during this talk I studied from the very high level, from the Java code till down to the native code, mainly to understand what's happening under the hood and to prove the optimizations. Otherwise, if we don't have a good experiment, it's still a guess. And my advice for you is always to be curious, to experience new things. Only being curious, only searching under the hood, you will understand the things in a better way. Thank you very much. If you have questions, I think we are a bit behind the schedule. No questions? Okay, thank you.